Note that to find the area between the exact integral and the estimate, we just simply find the difference and get the absolute value. The same thing for the midpoint rule. The purpose of the error bounds theorem is that we can even estimate the error without having the approximation of the trapezoid and the midpoint rule. The theorem guarantees that the error bounds will be less than or equal to these numbers. The constant k in the theorem is the upper bound of the absolute value of the second derivative. This absolute value of second derivative is a function, thus k is the extreme value of this function in the interval a comma b. Usually, to find the exact k, we would need to find the derivative of the absolute value of the second derivative, which is the third derivative of f. We then find the critical point and check the functional value of the absolute value of f double prime at critical points and the endpoints. Thus, oftentimes, we just simply use a convenient k instead of going through the trouble. Let's do an example. Given the integral from x equals 1 to 4 of the square root of x dx, calculate the midpoint using 6 subinterval and the trapezoid rule using 6 subintervals, then calculate any error bounds, and then calculate the integral exactly and verify that the error bounds are satisfied. It is best to draw a number of lines and obtain the x coordinates so that we can find the height in the midpoints and the trapezoidal rule. We take the interval 1, 4 and divide it into 6. The width of each subinterval is delta x, which is 1/2. The x coordinate are 1, 1.5, 2, and so on, all the way to 4. The midpoints of each is therefore 1.25. We then add a half to this 1.25 to get the next midpoint. So the next midpoint is 1.75. The next one is 2.25. Keep finding the midpoints until we obtain all of them. It is best to use fractions instead of decimal if we have non-terminating decimal. The midpoint rule is computed by taking the width 1/2, multiply the height using the midpoint for each. 1.25 is only the x coordinate, so the height is the functional value, which is the square root of x. So the height for the first midpoint is the square root of 1.25. The height for the second midpoint is 1.75, and so on. Each time we multiply 1/2 to get the area of the rectangle. The trapezoid rule estimate taking the delta x, which is 1/2, divided by 2 times f of x naught plus 2 fx1 plus 2 f of x2 plus 2 f of x3 plus 2 f of x4 plus 2 f of x5 and 1 f of x6. This is approximately 4.661488. Notice that these coordinates are the endpoints of each of the interval, and we use the left endpoint once and the right endpoint once. Any points inside the interval are being used twice, and these terms are the height of the functions, not the x coordinates. We still need to plug these x into the function given to obtain the height of the rectangles. Also, if we were to have the left sum for 6 rectangle and the right sum for 6 rectangle, then we can average the left and the right to obtain the trapezoid sum. Let f of x equals the square root of x, then the second derivative is negative 1 over 4 x to the negative 3 over 2. So the absolute value of the second derivative is positive 1/4 x to the negative 3 over 2. Since the derivative of the absolute value of the second derivative is minus 3 over 8 x to the negative 5 over 2, which is negative on the interval 1, 4, we see that the absolute value of the second derivative is decreasing, so its highest point must be on the left endpoint. That is, f double prime of 1, its absolute value, is the maximum, so k equals the absolute value of the second derivative evaluated at 1, which is 1/4. The k that we would need in the theorem is therefore 1/4. The error bound M6 is less than or equal to k of b minus a cubed over 24 n squared, but k is 1/4, b is 4, a is 1, and n is 6. This is 1/128, or approximately 0.0078. The error for T6 is less than or equal to k times b minus a cubed over 12n squared. This is 1/4, 4 minus 1 cubed over 12 times 6 squared, or 1/64, or approximately 0.0156. These are the error bounds for the midpoint and the trapezoidal rule using 6 subintervals. We can evaluate the exact value of the integral 1 to 4, the square root of x dx. It will be 2/3 x to the 3/2. Evaluate from 1 to 4. This is 14/3. The actual errors are: the errors of M6 is approximately the absolute value of 14/3 minus 4.669245. This is 0.00256, which is less than the error bound that we found, 0.0078. The error for T6 is approximately the absolute value of 14/3 minus 4.661488. This is approximately 0.00518, which is less than the error bound that we found, 0.0156. The actual errors are less than the error bound, so the theorem is verified.